in. And I'll share my iPad. So I think most of the material for next week's midterm will finish today, but there are there are a couple of things. Like on Thursday, if we'll probably finish everything like at the beginning of the class, but we'll still keep doing examples if we just end up earlier. So like we'll take this week just to do problems for the midterm. So before really we start with these sections, there's this somewhat weird topic about implicit differentiation that has to be mentioned at some point, and there's really not like a great place to mention it. So let's just like, it's like a band-aid, rip it off quickly, and like we can just be doing other things. So it is a little bit like in the middle of what I was saying last week, but we're starting today. Like I'll remind you in a couple of minutes where we ended up on Thursday. So just like a bit of a random topic, but it really cuts the flow of everything else. So like there's really not like a great place to introduce this, which is implicit differentiation. I don't know if you remember, like the good thing is like it's very similar to what you did in Calc 1, I guess. So let me remind, or maybe Calc 2, I don't remember where you do this. I think Calc 1. So if you remember from Calc 1, say you had like the equation of a circle, right? And like that secretly allows you to think of y as a function of x, right? So this would allow you to find the derivatives of y with respect to x. But the whole philosophy of implicit differentiation is that you don't want to do that, right? So here you can find dy dx directly. But there's like a more indirect route, which is it has the advantage that you don't need to solve for y. And so that's where the implicit differentiation kicks in. I don't know if you remember what you're supposed to do. In this case, it's like you take the derivative with respect to x on both sides of the equation. And after you do that, you get 2x plus 2y dy dx equals 0. And from here, you can solve for dy dx, and gives you minus what? Minus x over y. Is this okay? Does everyone remember? Does this look familiar? So far, so good. Good. So that's good. Now the whole point is that you can sort of do the same in this class. So here's like 251 version, or the multivariable version. So Calc 3 version. So now, like, for example, you could take the equation of a sphere. Right? Which involves x, y, and z. And again, if you really wanted to, you could just like think of z, for example, as a function of x and y, right? So you could like say, well, z is really like a function of x and y, which is plus minus square root of 1 minus x squared minus y squared, right? And so again, like from this perspective, you could find the partial derivatives now of x and y directly. So now you could find the partial of z with respect to x and the partial of z with respect to y directly. Is that okay? But the whole point of the implicit differentiation route is that you don't have to do this, right? Like you can do something similar to what I was just doing in the previous example. So let's do like the indirect approach. And so in the same way in which we differentiated here with respect to x, you could actually do the same in this case, but now you differentiate, like take like a partial derivative with respect to x on both sides. Okay, so you'll do something like this. Is that making so far so good? Are there any questions up to this point?
Could you please scroll up a little bit?
Yes.
Thank you.
Is there echo? I thought I was hearing myself, but maybe I'm going crazy. So any questions? And now, how do you find the partial derivative? It is like the same as before. It's 2x, right? Here comes like the important fact. This is like a partial derivative with respect to x, right? In this context, y is sort of independent of x because x and y are being regarded as the independent variables now. So you still say that the partial of y with respect to x is 0, but there's a partial derivative of z with respect to x, which is 2c. And this is the number 2. Is that making sense? So here, let me put it. The partial of y with respect to x is 0 because x and y are independent.
Professor?
Yes.
Couldn't you have just as easily set this up so that z and x are independent of one another and y is like the...
Right. I'm
y
actually
of
going
x
to
and
do it. That was my next example. Yes, like you can reverse the roles. Yeah, you can sort of decide which one you want to regard as the dependent variable and which two as the independent variables. But for now, in this context, x and y are like the independent ones, right?
Right. If I just see like d dx of the equation, like the second to last line that you wrote in the notes, how am I supposed to know like which one is independent and which one is going to be differentiated?
Right. That's a good point. Like the notation itself does not, like the way in which the notation is written, right, does not give you a clue on that. You have to sort of read the context of the problem, right? So the problem would say, well, you know, this equation somehow defines implicitly c as a function of x and y or something like that.
Okay, got it. Thank you.
It has to be given verbally somehow. Yeah.
Thanks.
So it's only because you wrote the initial
the
initial equation
yes.
with equal to z, the function of z.
Right. Like yes, like
that's what's implying.
Or like probably what they would like if you didn't want to write this, like they would say something like find something like this. I mean, if you already say something, if you write the instructions this way, right, it's telling you that, I mean, there are only 3 variables, right? And they're telling you like which of the variables is being thought of as a function of the other 2, right? That sort of closes the deal. Like that sort of pins down like what you meant, right? Is that making sense?
Yes.
But yes, some context needs to be given. In fact, otherwise you can run into many like weird stuff. I can mention, like, I like mentioning this example. Okay, maybe we should, I'll do it in a second. Like, I mean, it's always amusing. It always makes people concerned. It's fun. So you get x plus, you can divide by 2 on both sides. There's nothing, no, there's no greater or equal. It's all like an equals, I think. Is that better now? Or and then you can solve for the partial derivative. Is that making sense? And like, you can do something similar for the one with respect to y. So let me change colors so that it's better.
Wait, one quick question. Could you
Yeah.
tell me why dy dx of d dx of y squared was 0?
Oh, right. Like why this one is 0? Like the one in the middle, you mean?
Yeah.
The thing is that you're thinking of z as a function of x and y, right? When that happens, you think of x and y as being independent variables, okay? And so what that means is that I mean, like if a partial derivative is 0, that's another way to say that a variable does not depend on the other. And so in this context, like this is what I wrote here in red. The partial of y with respect to x is 0 because like x and y are thought of as not depending on one another. Is that making sense?
Is 1 second. So it's because they don't cross paths?
No, it is because like secretly, let's think about like the picture, right? Like this is really like the sphere, right? Like we're working on the unit sphere, right? So what I'm saying is like on the unit sphere, like what's going on when you think of z as a function of x and y, what that really means is that you take your favorite point x comma y, right? And that sort of like forces z to take a particular value, right? Which is like 1 minus x squared minus y squared root of that, right? But somehow you are sort of free to have chosen the value of x that you wanted and the value of y that you wanted, right? Like like it's almost like a bet, right? Like you are two friends and you are in charge of choosing the x values and your friend is in charge of choosing the y values, right? But you can sort of do that without communicating to one another, because once you choose your x value and your friend chooses the y value, we know what the z value is supposed to be, right? But knowing, like what I'm trying to say is like knowing what x is doesn't tell you what y is supposed to be. Is that making more sense now?
Yeah.
Like it is almost like independent information, right? Like if people in statistics would call them like uncorrelated, if someone wants to prefers that terminology. So it's I'm just saying like it is like two choices that you make on your like without having to think about the like one variable does not need to think about the other one, but z because of this perspective, the moment you know x and y, then that does force z to be whatever it has to be given by this equation. Is that better now? And so like here, like when you take the partial derivative with respect to y, then this one becomes like, it's similar, like x, this one becomes 0, and then this one becomes 2y, and the other one becomes 2z dz dy. Because again, we humans have decided which variables we want to regard as independent and which ones as dependent, right? And so this allows you to write something like this. Is that making sense so far so good with everyone?
So is this this is saying that the rate of change or the change in the slope along the surface of the sphere with respect to just the y variable.
Right, right.
Like,
Yes.
I guess I'm wondering like what this graph is just going to be a line or what?
Let me see if I can bring our friend GeoGebra to the rescue.
Like is that a
One
tangent?
question. It says fancy D over fancy D, right? And the squared one.
If fancy D over fancy D, yes. Here you mean?
Yeah.
Yeah. Like they look
First
like
I read like theta and 2. That's
they
why.
look like Halloween monsters. Yes. Like I don't know how they look like, but always think that they're like fancy Ds. Yeah.
Is the slope of the tangent line like along either like the x or the y direction?
Yes. Let me do a cute example. Okay. Let's see if this works. I'll show you GeoGebra. So we have our. Can everyone see GeoGebra here?
Yes.
So like what's going on, right, is that let's zoom in, zoom. So we have this, right? And then we have like, let's say I'm going to choose a point 0.5, comma y, comma 0. Okay, where is this? Okay, sorry, I should have, how did I call the slider? Sorry, it should have been, no, this is not the 0, comma a 0. Okay, 0, comma a, comma 0. Okay. I just need to do this. So there's, let's see. Okay, so there's this point A, which is below, right, on the XY plane. I don't know if everyone sees it. Let me do it like a bit more thick. So there it is, right? And I can, I can move it around. Okay, everyone sees it moving. There you go. So that's the point below, right? If you look at the coordinates, only the y is changing, right? So let me fix the animation. Like and then, but that gives you a point upstairs, right? Which is the point, let's call it B, which is like 0, comma a, comma square root of 1 minus a times a. So do you see like the point B? So when a is moving, right? When A is moving, like the corresponding point upstairs is moving. Does everyone see that?
Yes.
And so, you know, there's like this plane which contains like, this is like similar to the stuff about partial derivatives that we talked before. There's this plane which contains, which is parallel to one of the coordinate planes. So in this case, like you're moving Y. So X is fixed, so it should be like what, like the plane like X equals 0. Let's see if this is the one. Yeah. Okay. So there's this plane, right? That you get, and that cuts the sphere, right, into like this circle, right? So this point is sort of moving like on half a circle, if everyone sees that, right? And this one has a tangent line, and that's the one that the partial derivative we found computes. You know, like, so the partial derivative with respect to y is finding the slope of the tangent lines that you get here to this circle. Is that making sense?
Yes.
And so that's what's, and like, you know, there's like a similar story happening if you let the X move and other things, but that's like sort of what's going on in this case. So far, so good. Yeah, so like there's slopes, like you're finding slopes, but you have to think a couple of things. Like first, like you cut the sphere with a plane that gives you like a curve, and the slopes of those of the tangent lines to that curve are like the partial derivatives. Okay. But yeah, this is a fun thing to try. Good. Let me stop this and go back to the iPad. But like, yeah, like as someone mentioned, you can also, like, this is a bit more of a democracy. So you can think of you could also think of y as a function of x and y, of x and z. So like alternatively, right? Can think of y as a function of x and z, right? Because again, like secretly, this is our secret, right? Like we're not doing this, but we could if we wanted. You could also take the equation of the sphere, right, to say that y equals plus or minus x, like plus or minus the square root of 1 minus x squared minus z squared, Yes, like in most, I mean, like this is like, it all depends on the context. So that's what you're saying on the chat is true if you think of x and y as independent variables, so like look at what's going on, like what's going to happen here. So now you can think of now you can take the same equation as before, right? And you can take the derivative, like now y is a function of x and z, right? So now you can take the partial derivative of y with respect to x. And so what happens now in this context? Well, like the partial of x squared with respect to x is 2x. Now, before, right, we had said that the one in the middle was 0, but now the context has changed because now we're thinking of y as a function, like as depending on x. So in fact, now this is closer to what you would do in Calc 1. You write 2y dy dx. And now z is actually being regarded as independent of x. So now you put 0 here. Is that making sense? So you always need to be told which functions which variables you're considering as independent and which ones you're thinking depend on the rest. Is that okay? And so here, like you would say as before, then like this is more similar to the Calc 1 problem where like then now you would say that the partial of y with respect to x is minus x over y. Okay. So it all depends on which variables you think of as being dependent and which ones as independent. Is that okay? So like just to try to make this like more clear, like you could still take this one and like take the partial derivative with respect to z. And then now now x and z are being regarded as independent. So this one gives you 0. And now this one gives you 2y dy dz. And then this one gives you 2z equals 0. It is, you mean, why is this one, why is there a 0 here? Oh, because now y is being thought of as a function of x and z. So x and z are now being considered the independent variables. So this one is now because x, z are now independent variables. But that is not obvious. Like what I'm trying to say is that it's not clear which of the variables are become independent and which ones become dependent. When you do implicit differentiation, somehow the context tells you which ones you regard as dependent and which ones you regard as independent. Is that okay? Okay, so the whole point of doing this example is to show you, like in practice, how you can find the partial derivatives. There's a formula that the book uses, which you can use, which is fine. But like, I mean, in practical terms, like you can always find the partial derivatives this way. So I mean, like that avoids like memorizing one more formula. So you just take partial derivatives on both sides of the equation. You just need to remember which functions, like which variables are being considered independent and which variables are being considered dependent, okay? But if you do that, then there's not too much of a, there's not like a major complication. Is that okay? So far, so good? Oh, yes, sorry. Good. Perfect. Excellent, thanks. I agree. Anyone else? Is this okay? Good. Okay, so this is, again, as I said, this is sort of like a random topic, but this is essentially what you need to know. I guess I will try to, because there was a conceptual question today about the critical points, like let me try to get to that so that we can discuss what that was. So let's go back to what I told you last time. So last time I told you this thing about the directional derivative, and the directional derivative of a function in the direction of a vector was just the dot product of the function. Like it's the dot product between the gradient of the function and the direction given by this vector. So this is really like the formula that the most important formula that we discussed last time. Oh, sorry.
Why is the delta upside down for f?
Like this triangle, you mean?
Yeah.
Okay, so this is probably not the best, like so like the first thing you could ask is why you just use like this notation, right? The thing is that there there is a meaning for this later, and by later I don't mean in this class, but in higher math classes. So this means something different from this thing. It's not that it's obvious which one should have been called, like, you know, which one deserved like the upside down and which one deserved the normal one, you know. But like one got it upside down and the other one got it like in normal position. But this one is called the Laplacian. So so like the thing is like this, the other flipping it is reserved for something else. So it's so that it doesn't like interfere with it. But I mean, there's nothing too obvious about why you should use this triangle in front of f, right? It's just like a symbol that's given to it, you know, instead of writing grad f, like, you know, like yeah, someone asked like if this is a gradient. Yes, this is the same as saying like df dvf is grad f. I mean, it is the same formulas. These two things are this thing is like another name for this thing, right? The problem with writing grad f is that this is like less universal, right? You know, because like that's the difference between saying like, you know, it would be like the difference between saying that the circumference of a circle is 2 times pi times r versus like 2 pi r, right? Like pi written this way would have to be translated into all the human languages. In Japanese, you would write it differently. In Mandarin, you would write it differently. But it's similar to what happens here with grad. But like any country in the planet will recognize this as the gradient of f. But if you just write grad of f, then like that may not mean much to someone who does not know English, right? Is that making sense? Or Spanish, or most of the like Latin like origin languages probably will recognize this easily as gradient. But yeah, like there's no like, it's just that the other triangle is used for something else, and like, well, like whoever came up with this in the 19th century declared this to have like a triangle next to the f. So, but the gradient, yeah, like more importantly, the gradient I mean, like there are two, essentially the grown-up version would be something like this. Like if it's a function of 3 variables, it would be like this. And if it's a function of 2 variables, or like you can just copy the first 2 entries, right? Is that making sense so far, so good? The point is that I was explaining last time that the gradient is a vector, right? So the important thing from last time is that the gradient is a vector. Okay. And so as a vector, it has a fun feature that if you look at the level curves of a function, the gradient happens to be perpendicular to the level curves. So this is where we ended up last time. So like, again, what I'm trying to say here is that you can look at a function of 2 variables, right? Remember, level curves just means like the points where the function takes a specific value. So maybe I can think of this as a geography thing. So that means that on this curve, the function f takes a value 1. Maybe there's like a more interesting curve here where the function f takes like the value 7, right? And then there's like this other curve, like it would be a weird level curve, but I mean, it would be like a weird function for this to happen this way. And maybe this is where like the function takes a value 3. You see, so on each level curve, f is constant, right? And so the gradient happens, the gradient of the function f will be perpendicular to these level curves. So let's see, I have it here. Can everyone see GeoGebra?
Yeah.
So like, for example, this, like, again, like this is like, these are like the level curves of some function, right? So each of, like, they look like ellipses. They're not quite circles, right? But they're like X or ellipses. And so on each of these ellipse, like the function is constant, right? It has the same height. If you, that's, you can cheat a little bit and look at the perspective 3D, right? So this yellow circle, right? This yellow circle corresponds to one of these circles, right? And if you move the point, like, then you get like a different circle here, right? And so if you look at this animation, there's being drawn, there's like this vector that you see here, which is perpendicular to the yellow curve. It's too bad that they chose yellow for this animation. Otherwise, it would be nicer because yellow is kind of difficult to show on the screen. But so you see, like, as I move along a particular ellipse, you see like this vector just changes in direction so that it remains perpendicular to it. And I'm just saying this vector is our friend, the gradient.
One quick question.
Yes.
What is that plane that's moving along with it? The rectangular plane.
On the right hand side.
Mm-hmm.
Well, this will be what we call the tangent plane in a second.
Okay.
Right. Like, because, you know, like in the same way in which curves have tangent lines, surfaces will have tangent planes. And so this paper that's changing is also it would be like the tangent plane to the surface. But like, that's sort of like cheating because we're supposed just to look at the left side. But yeah, like that would be soon called the tangent plane. But everyone sees, like, as you move on a particular level curve, you get like this perpendicular vector, and it just happens to be the gradient. Okay. Is that okay?
I just want to check that, like, some intuition that came into my head is at least kind of right. I'm imagining like a gradient is in a sphere. I'm guessing. I don't know. If I think of like a balloon, there's pressure always going perpendicular to the surface of the balloon.
Right.
And there's always the elastic force pulling the balloon, trying to shrink it down to its original size.
Right.
Is that like, I don't know, for some reason.
So what you could say, I mean, eventually, what we would say, like, what will happen, this will happen towards the end of the course.
I also understand that we're not working with closed shapes always.
This like f, right, will later be interpreted as a potential function. Like, that's sort of like the same potential functions that you see in physics, like gravitational potential function and things like that, you know. And then the gradient of f will be the force. that's being acted on something. So so in a way, like if you thought the balloon, right, like you would like the function, like if you thought of the balloon as a surface with constant pressure, I don't know if that's maybe the best analogy, then the gradient of the pressure function would be like a force, and that would be pointing like towards the inside of the balloon or away from the balloon.
Yeah. Okay.
Yeah. But yeah, like later we will think about of F as giving you like some sort of potential function, and this will be related to whether forces are conservative or not. If you have seen this in the past. Is that making sense?
As a non-engineer, yes.
Okay, good. So right, and in general, oh, right. Someone asked me like if whether, and this maybe my answer could be weird on the chat. Someone asked me if there's participation grade on the Zoom meeting. I mean, there's really no, but like, I mean, like, I will remember you like nicely at the end of the semester, I suppose. Like, I mean, you know, like special cases, like, so like this, like this is not unique to level curves. Like if you, we also had talked about level surfaces, right? So the same happens for level surfaces. Meaning by that, I just mean that that if you have like a level surface, right? Non-level surfaces like are surfaces, right? So like this could be like this looks a little bit weird, but imagine like this is like a deformed balloon, right? Or deformed ball. This could be like all the points. Well, yes, a potato is probably a better picture of what's going on, right? Like this could be like the places where the, like think of this function as giving you like the temperature, right, at a point in space. So this potato would be all the points where the temperature is equal to 2, right? So what I'm saying is that if you look at that, the gradient of this function will actually be perpendicular to the potato. So here, like there will be like a 90-degree angle. So like a concrete example is that if you thought of like, just to like actually make a cute picture, if you thought of your function of 3 variables as being like x squared plus y squared plus c squared, I think we have seen before that the level surfaces were spheres, right? Like that makes sense. Here the level surfaces are spheres. And if you think about the gradient, right? What's the gradient of this particular function f? The gradient of this f is 2x, 2y, 2z. Yes. And so this is just saying that, sorry, that the gradient is looking like, in fact, this gradient is just like a multiple of x, y, z. So it's just saying like that the position vector is sort of perpendicular to like to a sphere. Is that making sense? Sorry, someone asked me to scroll up. So again, like the point is that you should think of the gradient as being perpendicular to a surface. Okay. where the function f is constant. So this could be like, again, like the level surface. And why is this useful? This is useful because it allows you to find tangent planes. So with this, you can find tangent planes. And that's how we wanted to really use this. Because if you have like to a level surface, I should say. Because if you have like a surface, like a level surface, again, like where like the function takes some particular value, right? And remember, like again, this is like the analog. I mean, this looks a little bit weird. This is like the analog of. Let's continue with the baked potato or whatever. This is like the analog of finding a tangent line, right? And so like the idea is like to this surface, you want to find like a piece of paper that barely touches the surface at each point. So maybe here you want to find like a tangent plane, and here you want to find a different tangent plane, you know. And here you would have like a different tangent plane, you see. So you want like you sort of try to like cover like the surface with a bunch of pieces of paper. And so the question is like, what was the key piece of data that you need to write the equation of a plane? Anyone remembers? Normal vector at a point, but actually the normal vector ends up being more important. Like the point usually is given to you. And so you need to find a vector that's perpendicular to the plane, but that should be like a vector that's perpendicular to the surface. And so, yeah, the key idea is that for finding the tangent plane, you use the gradient as the normal vector. So that's like all that you need to remember. So key idea to find a tangent plane, the equation of a tangent plane. You need a normal vector, and for that you can take the gradient. So what I'm saying is that the normal vector, which we called n before, n is just the gradient of f. Yeah, so let's say that let's do an example. So and I'll show you, this will be cute. I'll show you to you, like I'll show it on GeoGebra how this actually looks like. Let's see. So let me no, like you'll see it is, let's see. Okay, so let's say that, for example, let's say that the levels curve that we're looking at is like the function is this one. It's not too complicated so that I can plot it on GeoGebra. Okay, so and we're looking at the level surface of, okay, so this is the and the level surface is f equals 0. So that gives you the equation xy minus 2z squared equals 0. Okay. And so what's the point that belongs to this surface? Well, let's see. So the point, look at the point, find the tangent plane. To the point, to this surface. One, two, one. So the point has to be given to you at the point. Yeah. This is why I'm saying that like the part of the point is less crucial here. Sorry, just to go. Can everyone see like that's the, can everyone say the equation? Like this is like the equation xy minus 2z squared equals 0, right? So this is like the equation that like I wrote on the iPad, right? And then the point that I am writing is 1, 2, 1. And do you see it? Like it's this blue dot called A here. Does everyone see the picture? Like you have this point on the surface, right? And so we're going to try to find the tangent plane to it. How do I know that this point is on the surface? Just because it satisfies the equation, right? Like if you plug it in, it does satisfy, like minus 2z squared becomes -2, and then xy becomes 2. So minus 2 plus 2 equals 0. So that's why it satisfies it belongs to the level surface. So let's go back to the iPad. Right. So like the only thing that you need to do is find the gradient. So what's the gradient of f? The gradient of f is like y x minus 4c. Is that making sense? Because it's partial with respect to x, then partial with respect to y, and then partial with respect to z. And that's what you get. Is that okay? And so you have to evaluate it at the point P. So what's the gradient evaluated at the point 1, 2, 1? It is 2, 1, -4. Is that so far so good? And that's our normal vector. So does anyone remember the equation of a plane? It would be 2x plus y minus 4z. What do I have to put on the right-hand side of the equation of a plane? Anyone remembers this? Yeah. It's you can think of it as a dot product between the normal vector and the point. So this is 2x plus y minus z 4z equals 2, 1, negative 4 dot 1, 2, 1. So 2x plus y minus 4z equals 2 plus 2 minus 4. Oh, good. Oh, that's cute. So 2x plus y minus 4z equals 0. So that's like the equation of the tangent plane, okay?
Wait, Professor,
Yes.
where does the 2x come from above?
Well, it depends. Like, is this computation for the value of the gradient making sense?
No, I'm still confused there. I was trying to.
Is the purple thing okay? Is the
Yeah, the purple makes sense, and then the black makes sense too. But then the red that starts with 2x, like where did the 2x
Right.
come from?
No,
So
I still have a question. Like, where did you get the purple one from? Where was it?
the purple one?
Mhm.
The thing is like the function was so sorry, let me go up. Like the function was xy minus 2z squared, right?
Mhm.
So the purple is just the gradient of this function. Remember that the gradient was just like partial with respect to x, comma, partial with respect to y, comma, partial with respect to z.
Mhm.
And so the partial with respect to x gives you y, right?
Mhm.
The partial with respect to y gives you x,
Mhm.
and the partial with respect to z gives you minus 4z. Is that okay?
Yeah.
So the gradient, I mean, you always take the gradient of the function or the equation that you were given, okay?
Mhm.
And then you have to evaluate it at the point in question. The point is given to you, so you have to evaluate it at this point, which is 1, 2, 1. So that means substitute y with 2, x with 1, and z with 1, and that's how you end up getting this, right?
Yeah.
So far, so good.
Yeah. I
And-
think it just didn't make sense because like the first part of the purple was cut off.
Oh, I see. And then like this is like the ABC, you know, of the normal vector of a plane. So this is like AX plus BY plus ZZ equals. And that's how you get, like, that's why I get 2x here. I don't know if that clarifies that question about.
Yeah. Okay, thank you.
And this is not tangent, like this would, like regarding to the question of on the chat, this is not the equation of a line, this is the equation of a plane. So this would be the equation of the tangent plane at that point that 1, 2, 1. Is that okay?
I'm confused about the dot product aspect. So 2x plus y minus 4z is the dot product already?
Oh, this one on the left hand side, you mean?
Yeah.
Well, the thing is like if you remember the equation of a plane, sorry, like let me put it here. If you had like a point, maybe this is easier. If you had a point like x naught, y naught, z naught, right? And you had like a normal vector ABC, right? Then the equation of a tangent plane was ax plus by plus zc equals ax naught plus by naught plus c naught. Is that okay?
Yeah.
And so like it's just that the right hand side can be written as a dot product. That's what I did here. And this is also like a dot product between a, b, c, and x, y, z, right? So this is like, I mean, this can be also written as a, b, c dot x, y, z. Is that better now?
Yeah.
And yes, regarding the gradient, yeah, like the gradient, like, sorry, let me put it like on top here. The gradient is just partial of f with respect to x, partial of f with respect to y, partial of f with respect to c. So that's what I'm computing up like in the purple one. And yeah, this like let's go to GeoGebra. Seeing is believing. So what was the equation of the plane? It was 2x plus y minus 4c, right? Equals 0. And do you see it? There's your tangent plane. And so you see it touches the cone. It's supposed to be regarded as something that is tangent to the cone. I mean, this was like a cone, so it's sort of tangent to the cone at that point. Is that making sense? Let's do another one. So that to nail this down. So let's do another example, which is a little bit easier, but I mean it's okay. Let's like imagine that you were looking at a point. Another example. Imagine that you have the unit sphere. So here you have like x squared plus y squared plus c squared equals 1, right? And I take a point on the unit sphere. What could be an interest point on the unit sphere? It could be 1 over root of 3, 1 over root of 3, 1 over root of 3. So it's somewhere in here. So this is my point P. Is that okay? Like that it belongs to the sphere just because you see like if you plug that satisfies x squared plus y squared plus c squared equals 1, right? And so I'm just saying let's try to find the tangent plane to it. Is that okay? So what's the function in this case? What is f in this case?
Two x, 2y, and 2z.
Well, that's a gradient, right? Good, but yes, you gave me the gradient immediately. Like the function f is just like the function that defines the equation of the, right? It is x squared plus y squared plus c squared, right? And then the gradient, yeah, as you were pointed out, is 2x, 2y, 2z. Is that okay? And so the gradient evaluated at the point, right, is 2 over root of 3, 2 over root of 3, 2 over root of 3. And that's like the normal vector, okay? So far, so good. So this is our like the coefficients A, B, C of the normal vector, okay?
You would multiply it by the point?
I evaluated it. I mean, I plugged in 1 over, like, this is like the value for X, this is the value of Y, and this is the value of C.
Mm-hmm.
So I evaluated these numbers into the expression for the gradient.
Mm-hmm.
Is that okay?
Yeah.
And then, right, like once you know the normal vector, like the coefficients, like you can just write the equation of the plane as before is 2 root of 3x plus 2 root over root of 3y plus 2 over root of 3z. That equals what? Like, it would be two, like if you do the dot product or whatever is 2/3 plus 2/3 plus 2/3. So this would be 2x over root of 3 plus 2y over root of 3 plus 2z over root of 3. And 6 over 3 is 2. So the equation of the tangent, I mean, you can simplify, you don't have to, but like ultimately you can write the equation of the tangent plane as x plus y plus z equals let's see. I hope I'm not doing anything. Oh yeah, this is okay. I think this should be fine. So you can write the equation of the tangent plane this way.
One quick question. So why was it not, okay, so you put 2 over 3 plus 2 over 3 plus 2 over 3. Why was it not 2 over root 3 plus 2 over root 3 plus 2 over 3?
Oh, like here?
Just below that.
Oh, here.
Yeah.
Oh, here I'm doing like, that should be equal, sorry, this should be equal to the dot product. The thing is like I'm doing the dot product between 1 over root of 3, comma 1 over root of 3, 1 over root of 3, dot 2 over root of 3, 2 over root of 3.
Okay, makes sense.
Is that better now?
Yeah.
And that, like, that's what you get, like this sum. And then after that, I'm just really simplifying. Is this okay? So far, so good? So again, if you go to GeoGebra, sorry, just to do this quickly. If you go to GeoGebra, right, here you have the sphere, and then you have the point, which was 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. So you see the point A there, right? Like it's somewhere on the sphere. And then the equation of the tangent plane was square root of 3. There you go. Maybe this one is more clear than the other one. Is that okay? It's cool, right? And so why are we doing all of this stuff? The reason why we were doing all of this is so that we could talk about critical points and optimization problems. So this is like the last topic for the exam. We'll finish it on Thursday. I guess like the conceptual question, the first one, you can try to answer it, but I'll tell the grader to just take it. I mean, to just give everyone those points. But you should still think about it before. I mean, if you want, I'll still post the solutions for that one. But it's about critical points, so maybe I shouldn't include it today. So if you had like a function of one variable, right? If you were looking at the absolute max and min, not absolute max and min, just like the max and min, right? Like they sort of happen in the locations that I'm showing you right now, correct? If you think about it, like they are occurring where the tangent line is parallel to the x-axis. So here the tangent line is parallel to the x-axis, right? And when is the line parallel to the x-axis? When the line is horizontal, right? So line is horizontal. And so the slope has to be 0. And so f prime of x had to be 0. So that's how you found the critical points before. Is that okay? So far, so good? Good. But now, if you think about like our situation, now we don't have a curve. I mean, this is what we're going to do next time. We're going to find the max and mean of a function of two variables. So okay, this looks very amorphous, but imagine that there's like a peak here, right? There's like some weird peak here. There's some bottom at the curve, like at the end of the curve. You see, but hopefully, I don't know if it's clear. Like what I'm trying to find it are like the top, the peaks and valleys of this weird surface. The point is that like here, the tangent plane should be parallel to the XY plane. Like it should not be tilted. That should be like the condition for finding the max and the min. So here, like the tangent plane should be parallel. Is that making sense? So tangent planes shouldn't be tilted, right? So not tilted with respect to the floor. But should that mean? It should mean that the gradient is completely vertical, right? Like it's completely parallel to the z-axis. So you would like the gradient of f. Now we're looking at like a function of two variables. Like, sorry, I should have said this. Like we're looking at like the function of two variables. So you would like somehow the gradient of the function to be like aligned with the x-axis, with the z-axis. So we would like the gradient of f. So gradient of f should be parallel to the z-axis. Okay. But if you think about it, like the only way for that to happen is like, if you think of the z-axis, sorry, not parallel to the z-axis, but to the vector k, right? To the vector k, which is 0, 0, 1. But you know, like the only way for the gradient to be parallel to 0, 0, 1 is if the first two entries of the gradient vanish, and we need, so that means that the partial derivatives have to be 0. So I mean, sorry, I'm saying this a little bit quick, but I mean, sort of just to convince you a little bit. In practice, next time we'll just start from here, and like this is what you need to know. So what we really need, so we need the partial of f with respect to x equals 0, and the partial of f with respect to y equals 0. Okay. And this is like, and this will be sort of like our definition for critical points. So let me just write this more clearly. So like a critical point of f of x comma y, it is like a point where both partial derivatives vanish. It is a point where You can answer it. I'll just tell the grader to take it as an optional question. So like I'll make the second one worth all the conceptual points, like, and then if you get the first one right, like you get like some extra credit to the conceptual problems. Yeah. Like let's do that. Well, sorry, if by opposite direction you mean that that somehow it points like this, I guess that's what you're saying. That's fine. Like, yeah, it could point, right. It still would work. Yes. Like, well, how it ends up pointing depends on the specifics of the problem. But yeah. Like, it is fine. Yeah. The thing that really matters is that it's aligned with the z-axis. It doesn't matter if it points up or down. Yeah. Is that better now? So like, we have very little time, but at least let me do like an example, a very quick one of how you find critical points. And next time we'll do this all during class, like many times during class. So imagine that super easy one is like x times y. If that's the function, what are the critical points? Well, the critical points are solved by obtained by solving the partial of f with respect to x equals 0 and the partial of f with respect to y equals 0. So you always need to solve like a system of two equations for these problems. And in this one, what's the partial of f with respect to x? That gives you y. So y has to be 0 here. And x has to be, like the partial of f with respect to y is x. So x has to be 0 in this one. So what does that mean? That x and y are both 0. So the only critical point for this function is the origin. So is that making sense? And in fact, I'll return to this. Let me just put it on. I'll give you a second to finish. I'll write it first on GeoGebra, and so that way gives you like a second to type it on. Yeah. I don't know if everyone sees the animation. This is actually the graph of z equals x times y. So this is like the graph of that function. And the origin, I mean, the critical point is 0, 0. I mean, it doesn't, this is where the critical point is. And like, if you look at the tangent plane, it's actually z equals 0. So like, you can see it clearly from here. But like the cute thing about this critical point, like, is that it's like a potato Pringles chip, right? And I don't know if it's obvious, like if you put like a ball rolling from the top, right, it will just fall down, right? So there are directions where you can approach this point where you feel like you're going down, right? But there are other directions like this one, where if you put like a ball, in order to get to this point, you have to go up, right? So there are places where you have to come down, and there are other places where you have to come up to reach the point. So that means that like there are directions where it feels like you're like this point is behaving like a mean, and there are other directions where this point is behaving like a max. So this critical point will be called like a saddle point, because it's neither like a max nor a mean. But there will be other things like z equals x squared plus y squared, right? Where like the critical point will still be at the origin, but like the only way to approach it is like always by decreasing in height. So no matter which direction you take. So this would be like a max, like a mean, because you always have to decrease your height to reach it. And there would be other cases like the inverted salad bowl, where actually the critical point will happen here. And in order to reach it, you have to always increase in height. So that would be like a max. So basically what we are doing next time is like the version of the second derivative test. So we will classify the critical points as max, mean, or saddle points, essentially. Okay. So I'll repeat a little bit of this information because I'm throwing a bunch of stuff right now, but that's essentially what we're going to do. So I will just go back to the iPad in case someone needed to copy it. But think of saddle, like there will be max, mean, and potato Pringles chips, like which are the saddle points. So yeah, I'll see you on Thursday. Next Thursday we'll just do all of this.
Professor, I have two slightly unrelated questions.
Mm-hmm.
One is, how did you get so good at GeoGebra?
I mean, if that required talent, then like, I mean, GeoGebra is like the dumb, like, you know, it's like, have you seen like these books for dummies? Like, you know, like GeoGebra is like the dummy version of like MATLAB or Mathematica, which actually requires like some skills. Like in GeoGebra, you just type like the equation and you get it, right? So I wouldn't like it's.
I guess like I guess familiar with it is a better way of putting it then, because like it's every time I try using it, I'm always like, I can use the pre-published like models that people put on the website that
Like
you
the ones on the
with.
internet that I show you, you mean?
Right, like I can play with the ones that obviously like have pre-built sliders and stuff, but then entering in functions, is it just a matter of like remembering the notation for it? I know that it tells you the expressions that you need.
Right, it's kind of the notation, although again, it's kind of like, it's very intuitive, you know, like how you write it. It's not, have you downloaded the app or you're just playing with the online version?
I'm just on the online version.
Yeah, you should download it so that you get acquainted more with like how to type things. But I mean, it is pretty intuitive. It's not, that's why I'm saying like, it doesn't really require like that many skills. Like, yeah, sure. At the beginning, I guess like I also got tricked on how to, but I have, you know, used GeoGebra for many years already. So
yeah, it's just, you're able to float between like graphing 3D surfaces to doing parametric equations. Just
right.
like
I
really,
just like it because it doesn't require skills. And that's precisely why I like it. Like, it's not like MATLAB, which still, I mean, it's not that bad. Like, you know, all these programming languages, you get used to them. So it's fine. But I mean, if you're lazy, it's better just to use GeoGebra.
okay. The second question was when you set the derivative equal to 0, I think I heard in my economics class that was referred to as the first order condition. Is that correct?
Well, oh, you mean now for critical points or like even before that for the tangent planes?
Just generally referring to like the method of taking the derivative and setting it equal to 0.
Well, I mean, you could call it like that. It's like a fancy terminology by the economists, like, because, you know, if you think of, like, I'll erase this, but if, I don't know if you remember like Taylor's expansion, something like that. Like this was like Taylor's approximation.
Right.
There's like a version, like a grown-up Taylor version, which is similar to what you would expect to see. It's just like now you have to put like the partial derivatives, right? Instead of like
right. Okay.
and like, so, you know, if you find the, and it keeps going, if you ask the partial derivatives to be 0, that means like the linearization of the function is sort of 0. So it's like to first order, like the function is almost like constant. So I think that's like this thing about first order condition is probably what they are referring to. So I mean, it's not like a terminology that mathematicians tend to use, I would say. But you know, economists, like, they, like, for example, when they take derivatives, they like to put like the word marginal, I think, like marginal utility, right? They love coming up with their own words. So like, I think it's something similar to what's in this case. Like, they just want to use their own new word for it.
Well, that's kind of been part of my trouble in economics is I'm getting into the calculus with economics, and all of their math is basically just mathematics rebranded.
Yes, this is like, there's like a interesting history of economics, like to you know, like many of the social sciences to at the beginning, like certain traditions try to mimic just like the success of physics and like in building models. So I think there's like an obsession to some extent to.
I guess the same thing could be said for engineering, you know, velocity.
Right, although engineering, like the nature, I mean, like, you know, the nature of the engineering objects are still like more like unconscious, like that's probably like not animated creatures, right? Like without intentionality. The problem is that humans have intentionality, and like there's the mind and the mind body problem and all of these other things. So I'm just saying like but still like you, like for example, saying like the you can represent your preferences by a utility, right? It's like when you rate like a professor, right? Like you give like someone the number 9 and someone else gives the number 8, right? It is not clear at all how your 9 relates to that 8, right? Like,
Right.
I mean, just because you put like a number in front of something, like doesn't mean like it really means anything, right? And it doesn't mean like that if you had and another person gives 7, right? Like, so you have like 9, 8, 7. That doesn't mean somehow that the difference like in how you regard this person is sort of like increased by the same amount. You know, it's sort of very wishy-washy stuff. So, but somehow by putting like a number in front of it, you are supposed to be persuaded that it has like more of an objective status, right? There's like, but yes, there's like a philosophy, like there's like a more methodological problem there going on. Like, but it's okay. Like you should try it. I mean, there are things that work better, like for financial markets and things like that, because of just how like things have become like how these exchange stock values or whatever. But yeah, like they do have like a tendency where they just rebrand everything in their, it just sounds more fancy, like to say marginal utility function than just like, oh, derivative of the utility function. So
Got it. Okay. Thanks. Thanks
yeah,
for
yeah.
that.
Okay.
All right. Bye.
Bye.